chapter discusses concepts and the works of mathematicians such as Isaac Newton, Albert Einstein, Pierre-Simon Laplace, and Henri Poincaré. First, Isaac Newton, and independently the German mathematician Gottfried Leibniz, invented a new branch of mathematics, calculus. Calculus is a new area of mathematics concerned with the calculation of instantaneous rates of change. The physicists set out in search of further natural laws that could be used to calculate rates of change for natural phenomena. Heat, sound, light, fluid dynamics, elasticity, electricity, and magnetism were all used to find them. Second, the author discussed how Albert Einstein said that God does not play dice and how we really can determine how the universe works. This is by observing how the faucet drips in such a rhythm depending on how strong the flow is.
Then comes Pierre-Simon de Laplace's theory called the deterministic theory, where you can determine when the next drop will come out. Laplace is the great mathematical astronomer that wrote analytic theory of probabilities in 1812. However, after an experiment of a group of young graduate students at the University of California at Santa Cruz, it is only short-term predictability. If we try to determine more than 10 possibilities, we get so far from the initial results and the results become more inaccurate. This phenomenon is informally called the butterfly effect. It is when a system acts sensitively to initial conditions. The effect explains how small changes greatly affect the future and how it can lead to vastly different outcomes. It can also be called chaos. However, chaotic events actually follow deterministic laws, but to the untrained eye, it is indeed random.
There were developments in the category of chaos, and one of them is the geometrical visuals instead of numerical presentations. It is by Henri Poincaré, the French mathematician who invented the phase phase. The motions of any given dynamical system are represented by this hypothetical mathematical space. These ideas are to draw the attractors in the initial condition, which therefore will result in loops or curves using the old trick of coordinates. What we learn in this chapter is that chaos is well established as a mathematical phenomenon, and it has its own rather weird geometry. It is associated with curious fractal shapes called strange attractors. Also, it could be determined through a series of experiments. Statistics in chaos may rely on probability and their randomness, and may be called unscientific. However, they are actually not. For our closing statement, we would like to share a quote from the book. We used to think that simple causes must produce simple effects, implying that complex effects must have complex causes. But now we know that simple causes can produce complex effects. We realize that knowing the rules is not the same as being able to predict future behavior.